Hi. So this is compilers week 4. Retaping the lectures. This is Sherry Yang, since we had audio problems with the first lecture. So week 4's lecture, we mainly dealt with the top-down parser, but before we could even write one, we had to do some grammar modifications. And I reminded you about the schedule and what's coming up due and the tests coming up. And also, if you still don't have your lab 1 checked off yet, some of you have submitted it, but you haven't shown it to me yet. You will need to do that and show me how it works, and before you will get credit for the lab. So you can still do that either on Monday after class or on Saturdays in lab. So we reviewed kind of the roadmap for the compilers class, and this is the structure. We've already dealt with the preprocessor, the lexical analyzer, the tokenizer, also the symbol table. And those 3 boxes were all in lab 1. We have 3 different parts, but they really work together. The tokenizer and the preprocessor, they really perform pretty much the same functions. That is, they given a source program, those processes went through and break and determine what the tokens were. And if those tokens happens to be preprocessor directives like pound define, we did not handle pound include or pound if or if define or any of that in the lab itself, but pretty much all preprocessor directives, and you should know how they work. So we did take care of the pound defines, and that utilized the symbol table because that's where the symbols went. They had to be stored somewhere, and that was our symbol table. Now we're going to take those tokens. Okay, we didn't care how we got them. We just want the tokens now. We're going to feed them through the next part of the compiler we're writing, and that is the syntax analyzer or the parser. And we did that as part of homework 1. We pretty much took a grammar and we took a source program, and we kind of, we broke that into tokens sort of manually, and then mapped those tokens, that sample program, to the grammar and produce manually a parse tree. And that's the parsing process. And that process is exactly what our program should do. Our program should take a grammar and take a list of tokens and see if they match up. So parser is also known as a yes-no machine. Did those tokens or that source program match what we're expecting syntax-wise for the language? And that's what I had you do in homework 2, is you had to define what that syntax is. What statements are you going to allow? Are you going to have a for loop, or are you going to have a switch, or are you just going to have a while or if? What are the different data types? You probably should do more than just the int. The sample I gave you, the mini C, only had int. Well, it's not, it's one data type. So you probably should add a few more, a double, a string type, a character type, just make the program a little bit more interesting and useful. So that's what we're going to look at this week. Starting from this week is how to write one of these parsers. And when you're choosing parsers, there are really 2 main categories. Is it going to be a top-down parser, or is it going to be a bottom-up parser? The top-down parsers tend to be for smaller languages that are really easy to write. We're going to look at a couple techniques, the recursive descent, and then a table-driven parser, the LL1. But both those techniques use the grammar itself. We're not just going to ad hoc and decide, what goes where and what's allowed. We really rely very heavily on the grammar. Once we have the grammar done, then we can just turn to any of these techniques and just write it. So we need a grammar. We start with a draft, but depending on where you got the draft, we have to do some work with it to make it fit one of these techniques. And specifically, we're going to look at the top down first. And there are 3 things. I have 4 things listed here for modifications. Over the years, I've determined that the lambda productions are necessary. You just cannot get rid of them all. Yes, if your grammar did not have any lambdas, that would make it a little easier to parse. But if you didn't have any lambdas, then that means your programs could not have optional parts. If else statements is a perfect example. You don't always need the else. Sometimes you just have an if. You shouldn't be required to always put in an else. So that's not optional. Well, lambda handles the optional. You either have the else or you have lambda. That's optional. And parsing, like I said, is really just a matching tool. It's context-free because we don't really care about the context yet. Types. If it looks like a statement, but it's a statement. Even X was declared as int way earlier on. We'll have a technique. We'll have a way to deal with that. How do I know the X was declared as an int? Well, that's what we're going to bring back the symbol table a little later. So we can store that information in the symbol table. But the fact that X equals, quote, hello, is a perfectly legal assignment statement. It's not type correct, but we'll deal with the type correctness or the context later. Right now, we're just context-free. We just want to make sure it's syntactically correct, that I'm not missing a semicolon. I'm not, this is the format of an assignment statement, right? That's what we're concerned with right now. And in class, which we're not going to take the time to redo now, in class, I actually had you go through a couple very simple grammars. This one has AASC and a BBBB. So obviously the AAAA, BBBCC will parse just fine. The 2 A's matches the C at the end. The second 2 A's matched another C. And then, of course, you have the BBB and then the lambda. So we can take the input letters and map into this grammar and produce a tree, and it should just be 1. And the second example that I gave you in class to do was this expressions, the plus and the times. This particular grammar is ambiguous. Ambiguous means if I take A plus B times C and map it to this grammar, I'm actually going to get 2 separate trees. I could either take the plus first and then do the times, or I can take the times first and then do the plus. They will match, but one tree will be wrong in terms of operator precedence. And the fact that it's ambiguous means we cannot work with this grammar. This grammar needs to change. Next week's lecture, or week 5's lecture, the very first thing I did was I fixed this grammar. So we'll sort of hang on to that. And I had a handout of the Lua grammar and had you do a little bit of work mapping some sample code to the Lua grammar. Please refer to the handout for that, since I didn't have it in the slide. And so grammar, really, there are 2 formats as you search online. The context-free grammar is what we've been using in class, and that's the blue style here. You have a left-hand symbol and a little arrow. And then the right-hand side could be terminals, which are tokens, or non-terminals, which are what I call the big letters, right? Those were the big S and the big A's and B's that we were using before. And the terminals or the tokens were the little A's, the little B's. And so in this case, these are the actual keywords or parts of the programming language, like, commas and semicolons, things like that. Those were part of the language, and those were the tokens or the terminals. And there's another form called the Backus-Naur or the extended Backus-Naur form, and by Peter Naur and John Backus, the Fortran and COBOL people who designed Fortran and COBOL. They were the computer scientists. Noam Chomsky, who came up with the context-free grammar, was not a computer scientist. He was really studying languages and the complexity of languages. He came up with this language hierarchy. And they're actually work independently. They didn't know about each other. They didn't know they were doing the same thing. But they came up pretty much with the same notation to define programming language grammar. And I'm using the Lua example. So the top one, the black line here, that's the extended Backus-Naur form. In it, that brackets means optional, 0 or 1. And the curly brackets in the Backus-Naur form means 0 or more. Okay, 0 or more. That's the closure. As you know, that's the cleany closure. But it's also the recursive, right? Grammar is recursive. So if you want to recursively generate, A's, as many A's as you want, well, how would you do that? Well, you just have one symbol recursively generate itself. Then you get more and more and more. So here's an example of how I just map a Backus-Naur form into context-free grammar, which is what we're used to. And notice, by making a context-free, I had to introduce some other symbols. Okay. And here's another example using the mini C, again, using the Backus-Naur form, translating that into the context-free grammar. And so when we start parsing or build one of these top-down parsers, then we know it's context-free. Most programming languages is context-free. That means I'm actually writing a push-down automata. Right? Remember, finite automata was the tokenizer. That's for regular languages, for regular expression. Context-free grammar, context-free languages requires a push-down automata. There's some sort of a stack to keep track. And in programming languages, what are we keeping track? Well, begin and end. A lot of things have begin and end. So curly brackets, open bracket, close bracket. So those are things that we're keeping track of. And so for ideal grammar, and sometimes you may not get that just because the complexity of the language would be nice if you can have a unique rule for each type of token. One token, this is called one token look ahead. That means one token, one rule. I'm not going to have 5 or 3 or 4 different rules that starts with the same token. While in programming languages, think C. A lot of statements starts with type, like int. And a lot of statements, you have a identifier following the type. Int x, int function 1, int, whatever, double, whatever the type is with an identifier. So if they happen, if you have more rules that happen in, for a particular non-terminal symbol, they all start with the same token. It makes it hard to decide which rule you're going to pick. I have a type here, like int. Which rule do I pick? Well, if you pick the wrong one, then that means you're going to have to come back and try again, try another one, okay? Which then this process called backtracking, which will slow down your compilation process, which is probably not. You probably don't want to do that. So as much as possible, you want to factor out the common parts of the grammar. So if we take the Lua example, a statement could start with a keyword local as a token, the keyword function, or it could be a name. In this case, in the Lua grammar, name is just a user-defined name I call identifiers. Function body is a non-terminal, so we can go expand on the function body. Or name list is a non-terminal. We have to go look up what name list is, and the local optional. So clearly, if I pick local, the first rule, and turns out I don't have the keyword function, I have some other thing, well, I shouldn't pick that one. I should have picked the second rule. So I have to like keep local and come back to the second rule. So if I could factor that out, and then just so defer is also called deferring the decision till later. Okay, I have a local. All right, pick the rule local. And then you can decide whether you have a function or something else later to decide which branch you're going to go, right? So think of factoring as factoring out the common part, and then you can branch later. Okay, they both start with the local. Well, don't branch yet. Branch later. So that's the common part that we're going to take out. And how do we do that? Well, we factor out the local, and then we introduce a new symbol. Lack of creativity. We're going to just call it more local. What does more local have? Well, more local is what's left. Once you took out local, what's left? Well, function, name, function body, name list, local optional. That's what's left. That's what goes into more local. Okay. Okay, I'm going to pause this first part, and part 2 will continue on another video.